Okay, so previously we had investigated the total sum of the squares, the explained sum of the squares, the residual sum of the squares, and the standard error of the regression. This was output that we have obtained from R. Okay, and we verified these results then here in Excel. So the standard error of the regression we estimated as being 1.28. To understand the standard error of the regression, we should estimate the residual sum of squares. The residual sum of squares we had previously estimated as being the difference between the actual y, and then the y hat, which is the fit value. The fit is generated by the coefficients for the intercept and for the beta coefficient, the coefficient on the student-teacher ratio, the independent variable. So the best fit is this along the straight line here. Actual y is the blue point. The difference between the two is the residual. For each of the blue points, we square and then we sum all of those figures. We get the residual sum of the squares. The residual sum of the squares then is obtained by taking that sum, and then we want the standard error of the regression. We obtain that, the 17.128, the SCR, the standard error of the regression, is obtained by taking the residual sum of the squares. We divide by the number of observations, the number of x's that we have here, and we subtract away 2. So 1 over the number of n, 7 minus 2, that's 5. We divide 5 into this number here, take the square root, and we get the standard error of the regression. Now, ultimately, we want to take that value. Once we have obtained the standard error of the regression, we can then go on and estimate the standard error of the coefficient associated with the student-teacher ratio. Okay, so if we take that sigma, the standard error of the regression, and then in turn divide that by the square root of sigma x minus x bar to be squared. So recall, we've already estimated that the x minus x bar to be squared and sum. So let's just open it up for a moment and take a look at the formula. So we take the standard error of the regression, and then in turn we divide that by 75.93, which is the square root. So we're taking to the power of 0.5 means taking the square root, and the F9 here denotes the 75.93, the number associated with the sigma x minus x bar to be squared. Okay, so just to place this number in terms of the overall output from the regression, the 1.965, if we go into our data analysis, we observe that value here, and if we go into the linest, we observe the output also 1.96. So that is the standard error of the coefficient associated with the student-teacher ratio. Likewise, the same values observed here, 1.966. Okay, so a set of outputs, if you like. We have the explained sum of the squares, the total sum of the squares. We obtained the r squared by taking the explained sum of the squares, dividing by total sum of the squares. And then we found the standard error of the regression, which we used then to generate confidence intervals around the coefficient on the student-teacher ratio. So going back into Excel for a moment. So like before, the 1.96, the standard error on the student-teacher ratio, if we know the coefficient of beta and we know the standard error associated with the student-teacher ratio, then we can from those two generate the actual t-statistic just by taking the ratio. Okay, if we go back into the manual estimation, we can demonstrate a similar result here. If we take the beta estimate of the negative 2.96 divided by the standard error, we should get that 1.5099 or 1.51. Let's just make a quick comparison. 1.5099, 1.5099. Okay, so this is the t-statistic that's we obtain. We could round that to 2 decimal places, perhaps, or just have a higher level. Right, 1 is the same value here. This t value we generated here by making the same estimation. If we take the negative 2.968 and divide it by the standard error, we get the negative 1.51. Now, this value is quite low, and it should be normally higher than 2 before, as a rule of thumb, before we would start to consider it as having that this beta is discernibly different from 0. To investigate whether our beta here is statistically significant from 0, one of the relationships we can explore is construct a confidence interval where we take the negative 2.968, then plus or minus, and develop a critical value, a critical t-value that is with 95% confidence, and then multiply that by the relevant standard error. So for instance, we take the beta. So beta is, let's just highlight these, negative 2.968, negative 2.812, then initially minus, and then take C15. C15 is 2.57. We'll look at this in a moment. So 2.57, and multiply that by the standard error of 1.9656, and we get a value of negative 8.021. So this is at the lower end of the distribution for the t-distribution. And then at the higher end of the t-distribution, the upper boundary of the t-distribution is 2.085. How did we generate this? We took beta. So beta, this time we're adding. So plus the critical value 2.57 times the standard error, which we worked out, and that yields 2.085. And you can see that the boundaries here cross 0, and the range of values we have with 95% confidence crosses negative to positive. That means we may have 0 in that range. We do have 0 in that range, and because of that, we cannot rule out the possibility that the b value is equal to 0. In other words, not statistically significant. Let's look here at this t.5%, 0.025. What this represents is we're taking 2.5% in the tails of the distribution. So there's 2 tails in the distribution at the negative and the positive side of the distribution, and the sum of 2.5 and 2.5 is 5. So that's why we can legitimately say we're constructing a 95% confidence interval. The critical value here is we take t inverse. So just to read that, t inverse. The t inverse returns the 2-tailed inverse for the student's t distribution. And the syntax that we have here, T inverse is the probability and degrees of freedom. So the probability required, the probability associated with the two-tailed student t-distribution, and then degrees of freedom required, number of degrees of freedom with which to characterize a distribution. Okay, so we go back in, we just look here for a moment at the t value that we have here, and we use this, we identify the probability, the degrees of freedom, and then we use this value, the 2.57, to construct the confidence interval. Okay, so again, we use these t statistics. They're quite important when we're trying to interpret the relative merits of including a particular explanatory variable. Given that we've gerrymandered a little bit the numbers, we only have a few observations. Typically we wouldn't expect to see generate numbers that we can be really strongly statistically confident about, mainly because our degrees of freedom are very limited here. But more generally, to assert a particular statistical statistic, the 2.968, if we wanted to verify that we were somehow confident that this was statistically different from zero, we make reference to the t-statistics. The rule of thumb, normally if it's more than 2, where we have a reasonable sample size, then we should be relatively happy. But in this instance, it should be greater than 2.57 because our degrees of freedom are very reduced. To get the p-value here, we would invoke the t-distribution, open. We would take the positive value here. We would then identify the number of degrees of freedom, and then is it a two-tailed test? Yes, we'll take a two-tailed test. And then when we return that, we get a p-value that's equal to 1.9144. Again, if we go back to our data analysis, we can see we can copy this value here. This is the coefficient on the student-teacher ratio, the standard error 1.96, the t-stat, and then the p-value is 0.19144. That's greater than 0.05, so we probably wouldn't be comfortable with this value. Notice also, if we take these values and just look at the upper and lower bounds that we have obtained in the data analysis in Excel, if we paste these values here and just observe the t-statistic, the p-value is the same, right? 0.19144, and that was also shown to be consistent with the f value when we ran the ANOVA analysis in R, and we also got the p-value for the f value. The p here is 0.1914, so that's consistent here, and also consistent with the number, the p-value that we manually generated in the Excel estimation here. So overall, what this offers is a way of demonstrating how to estimate the intercepts, the coefficient on the student-teacher ratio in our relationship. When we were able to estimate the explained sum of the squares, the total sum of the squares, and the residual sum of the squares. We were able to estimate the R-squared, the standard error of the regression, the standard error associated with the coefficient on the student-teacher ratio. We generated a confidence interval using T, where we had 5 degrees of freedom at 95% level of confidence, and we were able to discern how statistically significant the b-value was in this instance, because it was in excess of 0.05, not extremely powerful. And again, we replicated those results in the ANOVA test and the R output.